All right, here we go. Relative motion. I'm really becoming conscious of how much hair I'm losing. I wonder what I look like at the time you're watching this video sometime in the future. Ugh. All right, sorry. Self-conscious moment that you just got to witness. All right, so here we go. So we're going to learn about relative motion today. All right, and so this is actually a really, really small part of the AP exam. Odds are it'll probably be one multiple choice question, but every once in a while it shows up on an FRQ. And it's never hard, but you have to understand the basics of it. All right, so what we're going to see is there's basically 3 or 4 different types of problems that we need to learn to navigate. And so I'll kind of show you what those 4 types are here, and through the homework, obviously, you'll get to practice that, right? All right, so here we go, relative motion. So here is the deal. I actually am really happy with the start of these notes. You ready? Sometimes a thing is moving on a moving thing. Sometimes a thing is moving on a moving thing. For example, Roy could be moving while he's walking towards the back of a bus, which is also moving. So Roy's walking, but he's on a bus, and the bus is going that way, right? Okay. Maybe Dennis is running on one of those moving sidewalk things that they have at the airport, those little conveyor belts that run on the floor, right? Maybe somebody's in a hot air balloon that is rising, but they throw a ball down out of the balloon, or up, right? Because then you've got a ball which is moving from a moving balloon, okay? Similarly, maybe a pen is being tossed into the air while you're in a moving elevator, right? Okay, so that's what it would look like in 1 dimension. In 2 dimensions, maybe Sally's walking across the aisle on a moving train, right? Or maybe a boat is crossing a moving river. Or maybe a bug is crossing a conveyor belt, right? The conveyor belt, and you got a little bug crossing it, okay? Or maybe there's a plane flying through a crosswind, all right? Or maybe a pen is being tossed in the air in a bus that's moving sideways. Okay, so there's a bunch of different examples, right? Okay, so how do we navigate these? How do we solve these problems? So first of all, let's take a look at a 1-dimensional motion. All right, so in this one, we've got Roy walking towards the back of a moving bus. All right, so it says the bus is moving across the ground. All right, so we would say that it is moving relative to the ground. All right, so suppose I told you that the bus is moving relative to the ground. It's moving forwards at 15 miles per hour. So the way that we're going to write this is we're going to write the velocity of the bus relative to the ground is 15 miles per hour. And it's forward, so I'm going to draw a little arrow so I can keep track of that and put a little plus sign there to, just to communicate that I thought about the sign. All right. Now, meanwhile, Roy is walking around, right? So let's see. So it says now Roy is moving across the floor of the bus. So suppose he's moving. Yeah, right. So he's walking on the bus, right? So his motion could be described as either relative to the ground or relative to the bus. So suppose he's walking towards the back of the bus at 4 miles an hour. I wish I'd written it that way. He's walking toward the back of the bus at 4 miles an hour. So he's getting, so that is the velocity of Roy relative to the bus, but it's 4 miles per hour negative because he's going towards the back of the bus, right? These arrows are not to scale. Maybe I should fix that. Whoop, there we go. All right, so the question then is, what is Roy's velocity relative to the ground? So here's the equation. So the velocity of Roy relative to the ground turns out to be the same as the velocity of Roy relative to the bus plus the velocity of the bus relative to the ground. So notice the way these letters are sequenced. Here we've got Roy relative to the ground, and my equation begins with Roy and ends with ground, right? Whoop, 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 like that, right? And then these middle guys are both the same thing, right? So I don't want to say they cancel because they're not really canceling, but if it helps you kind of memorize the order of the equation, whatever variable is in the middle here is going to sort of cancel, and then you're left with the 2 on the end. So here's my equation. I'm going to go ahead and put in some arrowheads because I didn't do that before. So the velocity of Roy relative to the ground as a vector is equal to the velocity of Roy relative to the bus plus the velocity of the bus relative to the ground. So for us, what's that going to be? Well, Roy is moving backwards by 4 miles every hour in a thing that is moving forwards 15 miles every hour, which means Roy has sort of a net velocity of positive 11 miles per hour forwards, right? Okay. So hopefully that makes some sense, right? The bus is moving forwards at 15 miles an hour. He's going that way at 4 miles an hour, sort of canceling out 4 of those 15 miles an hour, and we're left with 11 miles an hour. Okay? So that's how that works. Now, a thing that you need to get in the habit of, especially as these problems get more complicated, is before you start the problem, I want you to give me a little, like a legend, all right? There are 3 objects in this problem we care about. There's a bus, there's Roy, and there's the ground. So tell me that before you start the problem. So that way I know what your letters are. All right? That'll be especially important. In a minute, we're going to do a problem about a bug crossing a conveyor belt. And so both bug and belt begin with B. So I need to know when you write down B, what does that mean? All right? All right. All right. So here's sort of our general equations. All right. So this is the one that we just used, this velocity one. And honestly, this is the one that comes up the most often. Right? And notice the velocity of object A relative to object C, A relative to C, and the B's kind of cancel, right? What are objects A, B, and C? I don't know. It doesn't matter. That's how the equation works, right? I will tell you, though, 9 times out of 10, object C is the ground or the earth or the floor. All right? So here's our velocity equation for relative motion. All right? Now, it works for the other variables as well. Position. So I've used R for position here instead of, X, because it doesn't necessarily have to be on the X-axis. But it's the same thing, right? So the position of Roy relative to a flagpole is the same as the position of Roy relative to the fountain plus the position of the fountain relative to the flagpole. Okay, so you're just adding vectors, which brings me to an important point. Because my smart notebook software is stupid, it doesn't let me put arrowheads in. So all of these quantities here are vectors. All right, so we're not just adding numbers, we are adding vectors. So we need to think about direction. All right, and so the same equation works for acceleration. The acceleration of object A relative to object C is equal to the acceleration of A relative to B plus the acceleration of B relative to C. But note, suppose, look at this little example here. It says, note what this means about the acceleration if you're in a vehicle moving at a constant velocity. For example, suppose you're in an elevator moving up at a constant velocity and you toss a ball into the air. So what are my 3 objects here? So I'm going to have, let's see, E for elevator, which I'm going to abbreviate, B for ball, G for I don't want to use G because that'll be gravity. Yeah, we'll do it, whatever, ground. All right, so what this means is the acceleration of the ball relative to the ground is the same as the acceleration of the ball relative to the elevator plus the acceleration of the elevator relative to the ground. But look, it tells us here that the elevator is moving up at a constant velocity. That means the acceleration of the elevator relative to the ground is 0, which means the acceleration of the ball relative to the ground is the same as the acceleration of the ball relative to the elevator. Well, when you throw a ball up into the air, what's the acceleration relative to the ground? They're both negative 9.8 meters per second squared. So what this means is if you're in an elevator and the elevator is moving up at a constant velocity, you can throw something up into the air and it behaves exactly the same as it would if you were standing on the ground, okay? As long as the elevator is not accelerating relative to the ground, okay? Now, if the elevator is speeding up or slowing down, then things get wonky and then you got to deal with this, all right? There you go, all right? So let's see if we can apply that in the form of an example. Before we do, really quick side note. It's also worth noticing that the velocity of A relative to B as a vector is the opposite of the velocity of B relative to A. So here's an example. When I was a kid, we used to always go on road trips, and I'd lay in the back seat because I was an only child, and I'd look out the window and watch the trees go by on the freeway, right? So I'd be laying in the back seat, and I'd be watching the trees go, like that, right? So the trees were moving backwards relative to me, which means that I was moving forwards relative to the trees, right? So the velocity of u relative to the trees is 50 miles an hour. That means the trees are going 50 miles an hour backwards relative to you, right? Okay. All right, so now let's do an example. All right, so you are in a window cleaning elevator, which is going down at a constant velocity of 4 meters per second, presumably relative to the ground, right? So let's make a note here. So in this problem, E is going to be, oh, I want my pen to be a little bit fatter. This is bumming me out. Whoop. Okay, so E is going to be our elevator. You're going to throw a squeegee. That's one of those little cleaning things, right? S is going to be our squeegee. And then I guess we'll use G for ground. All right. So the velocity of the elevator relative to the ground is negative 4 meters per second. I'm going to draw a little arrow to indicate the direction. All right. The velocity of the squeegee relative to the elevator initially is positive 12 meters a second, right? Because it says you throw a squeegee up into the air at 12 meters a second relative to the elevator, okay? All right, if at the instant you release the squeegee, the floor of the elevator is 25 meters above the ground. I'm not going to worry about that because we don't need to get all funky with the notation. So the instant you release the squeegee, the elevator is 25 meters up and the squeegee is 2 meters above the floor. All right, so question number 1, what's the maximum height above the ground the squeegee reaches? So for question A, we'll do question A in red. For question A, we want to figure out what is the vertical displacement of the squeegee relative to the ground. Okay, well, let's see. What do we know about the squeegee relative to the ground? Well, the velocity of the squeegee relative to the ground initially is the velocity of the squeegee relative to the elevator plus the velocity of the elevator relative to the ground. Oh, well, that's 12 minus 4 equals 8 meters per second. So that's the velocity of the squeegee relative to the ground initially, 8 meters a second. When it's at its highest point, the velocity of the squeegee relative to the ground is going to be 0. The acceleration of the squeegee relative to the ground is negative 9.8 meters a second squared, and we're looking for delta y. So I'm going to use this guy. 2a delta y equals vf squared minus vi squared. Notice I know everything here except for my displacement. I'm not going to write out the math, but if you plug in your numbers, you will find that this displacement of the squeegee relative to the ground works out to be 3.27 meters. So that means my final height is going to be the 3.27 meters it went up, plus the 2 meters it started above the floor, plus the 25 meters that the elevator was above the ground, right? Those are those two numbers I ignored before, for a total of 30.27 meters. All right, so that's how high it goes above the ground. All right, now question B is almost the exact same thing. All right, so let me erase all this stuff. Whoop, whoop. Whoa. There we go. All right, so for question 2, we're trying to figure out the maximum height above the floor. So now we're looking for our vertical displacement of the squeegee relative to the elevator. All right, so now all I care about is the squeegee in the elevator. So I don't even need this. All right, the velocity of the squeegee relative to the elevator is 12 meters a second when you first throw it. The velocity of the squeegee relative to the elevator final is 0 at the top of the path. It stops moving up. That's why it's the highest point. The acceleration of the squeegee relative to the elevator is still negative 9.8 meters a second squared because it's moving at a constant velocity. The elevator, right? That was what I talked about. Here, right? The velocity of the ball relative to the elevator is the same as the velocity of the ball relative to the ground because the elevator is going at a constant velocity. And we're looking for our vertical displacement. So you can use that same equation. 2a delta y equals vf squared minus vi squared. Plug in your numbers, and you'll find that your vertical displacement is 7.35 meters. So that's how far it moved up from where I threw it, but it started out 2 meters above the floor. So you get 9.35 meters. Okay, so there we go. One-dimensional relative motion. Now, it turns out it works the exact same way in 2 dimensions, but you just got to keep track of your i's and j's, right? You got to keep track of your direction. All right, now sometimes these problems work out really easily, and you're literally just adding i's and j's. Sometimes they're a little bit more complicated. All right, so here's your recipe for solving 2-dimensional relative motion problems. Okay. Step number 1: identify your objects. Tell me what the objects are, exactly like I did here with the elevator and the squeegee in the ground, okay? Step number 2, write down the given information, specifically focus on those velocities, because that's what usually is going to be the issue, okay? And what I want you to do is write it down in unit vector notation if you can. Write down the direction of the vector if you can. Like if you know that one of the vectors points straight up, then draw a little arrow. This has to point straight up. If you know the size of the vector, but not the direction of the vector, make a note about that, okay? Kind of tell yourself everything you can about each vector in the space, all right? The next thing you have to do, and this is huge, you have to write out the vector addition equation, okay? Remember, A relative to C is A relative to B plus B relative to C, okay? Write that equation out, because A, if you know everything in unit vector notation, now you can just plug in your i's and j's and solve it. If not, you have to make a drawing, but remember how the drawing goes depends on where the vectors are, right? Because these two guys are always going to be head to tail, and this guy is head to head at one end and tail to tail at the other, okay? And it says all that here. So VAB and VBC, the two guys that are being added together, they have to be head to tail, so boom, boom, right? Or, well, and rather, sorry, the resultant, the result of your two vectors that are getting added together, it has to be tail to tail at one end and head to head at the other. And this is huge, and I wish I'd written this in the notes, but it's important enough that I'm going to stop right now and say it. This is ginormously important. A lot of times your vector drawing is going to be a triangle. It will often be a right triangle. VAC does not have to be the hypotenuse. It is sometimes, but not every time. Okay, it's going to depend on where your vectors are. All right, so I'm going to do 2 more problems. They're both going to result in right triangles, which is all you really need to know for the AP exam. But be careful. In one of them, this vector is the hypotenuse, and in the other one, it is not the hypotenuse. All right, so let's pay particular attention to that in these next 2 examples. If you need to, pause the video right now, go grab a Kool-Aid, and then come back, okay? Because this is big. All right, so here we go. Example number 1. These are both a bug crossing a conveyor belt, but with different goals, all right? I like the bug crossing a conveyor belt example just because I think it's easy to visualize, right? You've got the conveyor belt going, and the bug is crossing it, okay? It's the exact same thing as a boat crossing a river, except you've got a boat instead of a bug and a river instead of a conveyor belt. It's also the same as a plane flying through the wind, right? Instead of a bug, you've got a plane, and instead of a conveyor belt, you've got the wind. Okay, but they're all really the same exact problem, okay? All right, so here we go. So we've got a belt moving relative to the floor. The belt is moving to the right at 3 meters a second, and then the ant is crossing the belt. So let's start. We're going to follow our little recipe here. Identify and name your objects. So in this problem, here are my 3 objects. A is going to be the ant, B is going to be the belt, and then we'll use F for the floor. Sure, we'll do F for the floor. You could use G for the ground, whatever. All right. So the belt is moving to the right at 3 meters a second. Doot, doot. So the velocity of the belt relative to the floor is 0.3 I meters per second. Cool. All right. So that's that. then it also tells us that an ant is trying to cross the belt, right? So the belt is going this way, and our ant's trying to cross it, right? This is top view. So here's my belt, and here's my ant, right? Okay, so the ant wants to cross the belt, so he crawls up, like this way, across the belt at 4 meters a second. So here we go. So the velocity of the ant relative to the belt is 0.4 meters, 0.4 j meters a second. He's crawling that way, right? All right, and so the question wants to know, I guess it didn't explicitly ask it, but it says clearly the ant is moving relative to the floor. So the question is, what is the velocity of the ant relative to the floor? All right, so let's go back to our little recipe here. So I already identified and named my objects. Oh, I wrote down 2 of my 3, but the third one is the one I'm looking for, right? So now my next step is going to be to write down this equation. This is huge, okay? So here we go. So I'm on step 3. Let's write down the equation. So the velocity of the ant relative to the floor is equal to the velocity of the ant relative to the belt plus the velocity of the belt relative to the floor. Now notice vector hat, vector hat, vector hat, vector hat, vector hat, right? So the velocity of the ant relative to the belt is 0.4 j meters a second plus the velocity of the belt relative to the floor is 0.3 I, 0.3 I meters a second. That's it, we're done. That's the velocity of the ant relative to the floor. The velocity of the ant relative to the floor is 0.3 I plus 0.4 j meters a second. And technically we're done. But we should dig in and figure out what the curse word is going on here, right? What's really going on? So here's the deal. 0.3 I meters a second. Well, that's the velocity of the belt relative to the floor. So that's this. Now this is head to tail with the velocity of the ant relative to the belt. That's 0.4 j meters a second. So here is the velocity of the ant relative to the floor. So do some Pythagorean theorem, and we'll figure out that this is 0.5 meters a second at, if you do the trig, this turns out to be 53 degrees above the positive x-axis, okay? So technically, I guess I sort of made this triangle upside down. So I guess what I probably should have done if I'd wanted to make an accurate drawing, not accurate, a recipe following drawing of it, then what I would do is this. I would go, let's see. So we're going to color code. So the velocity of A relative to B, 0.4 meters a second is the velocity of A relative to B, right? And then the velocity of the belt relative to the floor is 0.3 I. Notice those are head to tail. And then my resultant vector, the velocity of the ant relative to the floor, it's a 3, 4, 5 triangle, so it turns out to be 0.5 meters a second at, and I guess you'd then have to find this angle, which is the same as this angle, so 53 degrees above the positive x-axis. All right? Cool. All right, let's do our last example. All right, now, so, notice here on this one, my resultant was in fact the hypotenuse of my triangle because it's across from the right angle. That is not always the case. And in fact, these triangles technically don't even have to be right triangles. For the AP exam, more than likely they will be, but they don't technically have to be, all right? Okay, so now, suppose the ant doesn't want to move to the right. Suppose he wants to literally just go straight across so that he's looking across that conveyor belt and he sees the Twizzlers on the other side of the checkout lane. And he wants to go straight towards the Twizzlers. He doesn't want to get carried kind of down along with the belt. All right, so suppose the ant doesn't want to move to the right. In what direction should the ant crawl so he doesn't move left or right? So here is what we know. So I know that the velocity of the belt relative to the floor is still 0.3 meters a second I. Okay, and I know that the velocity of the ant relative to the belt is still 0.4 meters a second, but I don't know what direction he's crawling in. Okay, and my goal is I want the velocity of the ant relative to the floor to be straight across, right? So the belt is carrying him this way, he wants to go straight across. All right, so I've labeled my 3 things, right? Like I already identified my objects. I wrote down as much as I could about my velocities, but I don't know the direction of one of them and I don't know the magnitude of the other. So I can't do the math using this equation. All right, but let's write down the equation. So once again, we've got velocity of the ant relative to the floor equals the velocity of the ant relative to the belt plus the velocity of the belt relative to the floor. So I'm going to draw this because I can't do it using my vector or my IJ notation. All right, so this guy has to be my hypotenuse. Ooh, shoot. All right, so this one has to be my resultant, right? So let's go ahead and draw that in. I guess I should color code. So here we go. So this guy's going to be in purple. All right, so that's got to be tail to tail at one end and head to head at the other. All right, now this guy here, I know the length of it, but I have no idea what direction it goes in. Okay, this guy, I don't know anything about it, so I can't draw it. So I guess that leaves me trying to draw this guy, VBF. Oh, well, I know that is 0.3 I meters a second. And since this guy has to be head to head at one end and tail to tail at the other, here's my VBF. VBF equals 3 meters a second, which means the red one, the missing 0.4, must be this way because the red and the blue have to be head to tail. So VAB is 4 meters a second. Sorry, 0.4 meters a second. And this was supposed to be 0.3 meters a second, right? Oh, cool. So now I can find this missing purple side, this other side over here, right? So I wasn't smart enough to do that. I'm going to grab a calculator real quick. What do we got? 0.4 squared minus 0.3 squared. Boom, square root. So it looks like his velocity as he goes across is going to be 0.265 meters a second. What direction should he crawl in? I guess I should find this angle, which is the same as this angle. So this is 0.3, this is 0.4. I want this angle. Here's my right angle. So I guess I want the inverse cosine of 0.3 over 0.4. So second cosine 0.75, sorry for not having this, is, oh, that's in radians. So 41.4 degrees. I guess above the negative x-axis. Right? So that's this angle here, and it's telling us he wants to go that way. All right, now notice, I just realized I forgot to do a thing. It says, how long will it take the ant to cross? Well, the time it's going to take the ant to cross is going to depend on this vertical velocity, right? Because he's trying to go vertically across the belt, right? So to find his time to cross it, I'm just going to go, okay, vertical displacement is vertical velocity times time. So he needs to go 0.6 meters at a rate of 0.265 meters a second for some number of seconds. So divide both sides and you get 0.6 divided by 0.265, so you get like 2.26 seconds. All right, it's going to take him, yeah, good. Now, I forgot to do this on the previous example. Here I didn't solve for how far he's got to move to the right. So let's do that real quick. So what's happening here is you'll notice the ant is going at 0.4 meters a second across the belt, right? He's going faster. So now it's not going to take him as long to cross, right? So now I'm going to do this. I'm going to go, all right, my vertical displacement is 0.6 meters, but now with the vertical velocity, 0.4 meters a second. So the time, if you find it, is only going to be 1.5 seconds. So how far does he move to the right is going to depend on the horizontal velocity, right? So my time is 1.5 seconds. So now my horizontal displacement is Vx times t. The belt is moving at 3 meters a second, sorry, 0.3 meters a second, and he's going for 1.5 seconds, so he's going to go 4.5 meters to the right before he gets across. All right, so that was a lot, but those are the only two types of problems you need to know, and the bell is ringing. You're going to have questions when I see you in class next time, so please come in with questions. We have to talk about this.